Hello everyone. So let's talk about this problem. Binary tree right side view. So the problem statement goes as given the root of the binary tree, imagine yourself standing on the right side of it, returning the value of the tree. You can see ordered from the top to bottom. So this is the example of the tree. So let's analyze it, what question is saying and how to implement it. So let's see. Uh, so yeah, let's see what is. Suppose first of all we have to make a binary tree. Not a binary tree, any tree. Suppose this is our tree and we are standing right side of this tree. So how this tree gonna look like to us? Suppose let's assume 1, 2, 3, 4, 5, 6, 7. Okay. So what is the first node from top to bottom we see if we are standing right side of the tree? So first we see 1. So 1. After that we see 3. So we put 3. After that we see 6. We put 6. After that we see 7. So we put 7. So it is basically this. If we are standing right side, so the others node is hiding from this part. So how can you imagine? Basically we can say it's, if we are standing the right side, the right side of the view will be look like this, something like this. Okay, so the left side nodes is hidden, is basically hidden. Okay, so if we make a right side view, this this is how it's look like. So this is our first node, this is third, this is sixth, and this is seventh. Okay, the others are basically hidden. So this is pretty much about that, how this problem looks like. Okay, so let's see how to solve this problem. So we have to print the right side view of the tree. So basically we have to print 1, then we have to print 3, print 6, and print 7. Okay, so how we gonna do that? So there, first of all, the first thing is, if we uh, traverse at if we are traversing level wise, so we see one thing. What is it? Key, if we are traversing left to right every level, so the node which are coming, we are traversing left to right. Okay, so the every node which are coming at the end of the tree, at the end of each level, suppose this is a level 1, level equal to 1, level equal to 2, level equal to 3, level equal to 4. So at the end, which node we are getting? We are getting 1. So we put 1 in our answer. Let's suppose, let's talk about level 2. So what is the last node which we are getting? Last node is 3. If we are traveling from left to right, left to right. Okay, if we are traveling from left to right, last node is in the second level is third. So we put 3 in our answer. Okay, 1, 3. After that we travel third level. So what is the last node we are getting? 4, 3, 6. So 6 our last node. So we take 6 and put it or put it in our answer. Okay, and if we are traveling level 4, what is the last node? Last node is 7. So we put it into our answer. So this is the level order if we are traversing from left to right in level wise. Okay, so if so the first thing which comes into our mind is BFS. BFS. breadth for search, which is generally known as level order traversal. Okay, so in BFS, we can the time complexity of BFS is basically big of n. We can find what is the node at the end of the tree, at the end of the level. If we are traveling left to right, be careful. If we are traveling left to right, if the order gonna change right to left, then right to left, then we will take the first node which comes into the level. Okay, so here we are traveling left to right. Okay, so the time complexity of finding out the answer, so it's big of n. But in BFS, we have to make uh, we have to consider a space complexity in which we have to take care of the edges, means the nodes which are at the level, which are currently at the level. So suppose we have to keep track of the nodes at every level. So in level 2 we have two nodes, so we need to store these two nodes in BFS. Okay, if we are at node if we are at level 3, we need to store both the nodes. So 4 3 6, so it is a complexity of approximately first complexity of uh, it's a GP formula basically. It's not, it is approximately, we can say it is 4 into n, but it is we can say it is a GP formula. So how can we calculate it? So it is basically every node. So at every level we are multi we are increasing nodes. So at level 1 we are for one node, at level 2 we are 2, at level 3 we are 4, at level 5 at level 4 we are actually having 8 nodes. So it's become 1 plus 2 plus 4 plus 8, and it's gonna infinity. Okay, suppose it's gonna infinity, so it will give it is look like a GP. So we can say, we can calculate what is the space complexity by calculating this. Okay, so what is the GP formula? GP, I think it is first digit. Suppose first digit we will take about x. Okay, so 1 minus r ki power n, r to the power n, 1 minus r, where r is the common difference between digits, which is basically 4 to 2 is the common difference. Okay, basically not common difference, we can say common multiple, something like that, and n is the how tail up to n. Okay, this is how we can calculate the space complexity, but for a rough estimation we are taking 4 into n, so it will take 4 into n space complexity. Now how to optimize this? We have time complexity of big of n, which is pretty much simple. We don't have we can't find our answer in big of n, so it is pretty much same. So we have to uh, deal with the space complexity. So how to deal with the space complexity? Okay, so let's see, let me rub this. So in previous video we will learn about let me delete this. Okay, let me rub this also. In previous video we will learn about let me write our answer will be 1 3 6 and 7. Okay, in previous video we will talk about how to traverse a tree. Basically there are three methods: pre-order, post-order, and in-order. Okay, if you don't know that, you can go to that video. Okay, go through that video. So let's see how our traversal technique will find this answer with a time complexity of big of n and with a space complexity of big of 1. Okay, so let's see how to. So in basically in post order we are usually perform what is the operation post order. So post order, the operation is, first of all we will uh, traverse to the left side of the tree, then right side of the, then root. Okay, so this is the post order traversal. So we generally do, uh, just for the example we are relating with the post order. So in post order we generally do right, left, right and root. Okay, so now in this question we have to travel with a different method. We have to travel, first of all we have to travel with the right side, then we go to the left. Okay, so this is the pretty much idea how to travel this tree. So let's do a quick code up. Mm, so let me, for saving time, let me paste the code. uh, it's not let me do something. So let's see, this is our code. So let's see how this code will find and how to dry run. Basically I do a dry run to better understand how this code will work for this problem. Okay, let me rub this. Okay, so we know that we have to first traverse to the right side of the tree, then left side. Okay, simple. So first of all, we we have to make, and for the answer we have to make our array or a vector. So we take a vector, okay, any data structure to store the element. So it's look like stack. So let's make it easier. It's a vector. It store our answer. Okay, simple. So let's see. This is our root node which we are going to pass. Which are going to pass. What is our root node? Root node is this. Okay, this is our root node. So this is our root node which we have to pass it in our function. Okay, this is the level. So what is the function of this level? This level actually take care of that if we are traversing to a level. Okay, if we are traversing to a level, so the other nodes which are behind our right side of the node, which will not get enters in our answer. So the work of the level is basically to keep track that our level, if we traverse to a level, then we basically don't put any other nodes from that level. Okay, it's simple. This is a vector which is, this is answer which is a vector form. Okay, so we will keep our answer in vector. Okay, so let's see, let's define a level variable. Okay, so first of all we have to pass our root node. So if root node is null, then it returns nothing. Okay, it returns back. If our level is equal to answer dot size, our, this is our answer. So our currently our answer having size which is, our level is also 0, this is also 0, and our answer size is also 0. So we put our root data into the answer, so which is 1. After that we will travel to the right side of the node and increase our level. So let's draw with the right pen, then we will travel right side of the data. Okay, after that we come back to our function, which we will, after that we will increase our level which is now 1. Now it is 1, it is after traversing one time. Okay, so it will become 1. Okay, so it is simple. Now uh, after that we will check our root node is null. Nope, root node is not null. Again we will check. Our level is equal to answer size. Our level is 1. Our answer size is also equal to 1. Then we will put our data 3. Okay, simple. Again, we will go traverse to the right side of the tree. This is right side. Okay, this is left side. Left side. Okay, again we will travel. Now again we will traveling, we will increase our uh, level by 1. So now the level become 2. So here the now level become 2. Okay, so our root node will become, let me draw it with red pen. So our root node become 6. So our root is not equal to none. That's fine. Level is equal to answer dot size. Yep, level is 2 and answer dot size is also 2. So we will put our root node, which is 6, inside the inside our answer vector answer. Okay, simple. It's putting 6. Okay, after that we again travel to the right side. We will increase our level by 1, so it will become 3. It will become 3. So after traveling right side of the, suppose there is nothing. Okay, so after that, if we are traversing to the right side of the node which is having data 6, so we will get nothing, which is a null value. So it will return data, it will return nothing. Okay, simple. It will come out from the data. Okay, so let's again backtrack, basically not backtrack, it will come back to our root node after returning. Then after also returning, it will come, no, from that it will, after that it will come to our right node, then it will pass to the left. Okay, so left side is also null, left side is also null, which will gonna return. Again it will check left side, again it will gonna check left side of the of this node, which will return null. Again after coming to the our root node, it will check, it will go to the right side of left side of the node, it will check, yep, it is not null. Now again our level will become 1. How our level become 1? Initially we pass with level 0. Okay, initially we pass our level with 0. So after coming to the root node, we got our level 0. Okay, simple. So now we travel right side completely. Now we have to travel left side. Okay, left side. So let's see, now we are traveling left side. So uh, when we travel left side, we will increase our level by 1. So similarly increase level by 1, it will become 1. And check, our root is not equal to now it our root is not equal to null. After that we will check whether level is equal to answer dot size. Our answer dot size is currently 3. Okay, our answer dot size is currently 3, but our level is 1. So we will not push our data. So we will not push our data because 3 is not equal to 1. Okay, so we will not push our data. Currently array dot size will be 3. Okay, so we will not push our data. Again after traveling to the left side, it will go right side first. Okay, so it will travel right side. Let me check, it will travel right side of the data. Let me rub it. Okay, it will go right side of the data. Again we will check, our root is not equal to null. Yep, this condition is true, and this condition is false. Sorry, this condition is false. Again we will check our level is equal to answer dot size. Level is our currently, we will increase our level by 2. Now level by 2. So again we will check, our level is equal to answer dot size. Not, it is not equal, 2 is not equal to 3. So we don't push any data. Simple. Again we will come back because it is having a node which is which is the root node which is equal to null. So we will return back. Again we will come back. Let me again it will come back in the data of the level will change. Level should be 1. Okay, after coming back it will go to the left side of the node. Okay, so after that it will go right side of the node. So let's travel right side, sorry, left side of the node. I'm sorry. So after going to the left side, it will check whether our root node is null. Yep, root node is not equal to null. Then it's come to the next statement, which is level is equal to answer dot size. So after traveling this, the level should be changed. Level should be 2. Okay, so no, that array dot size or the level is not equal. So we will don't push any data. We will travel to the right side of that node. Simple. Okay, we will travel right side of the node. Right side is null, so we have nothing to do. We will come back, and after that we will travel to the right side of that left side of that node. So we will travel left side of that node and increase the level by 3. Okay, increase the level by 3. Now it will increase the level by 3. Now we will see our root is not equal to null. Yep, it is, condition is true, our root is not equal to null. Now we will check level is equal to answer dot size. So our current level is 3 and our answer dot size is 3, which is equal. Okay, so we will put data which is 7 into our answer array. Simple. Okay, now we will come back again. Our level will decrease it by 2. Our level will decrease it by 2. Again we will come back. Our level decrease it by 1. Our level decreases by 1. Again we will come back. Our level becomes 0 again. Our level becomes 0 again. So we will get our answer here. So this is a simple traversal technique in which we need 3 things: a root, level and answer which we will gonna store in a vector form, level which keep track of every level, that there is no two node present from the same level. Okay, so basically it keep track of that point. Again root which we have to pass. Okay, so let's try to code it, how this code gonna look like. So let's try to code it. So we have given a vector, we have to answer return a vector. So basically let's make, first of all we have to make a vector of integer type which is having our answer, and after that we have to return that vector also. So now we're gonna make a function. Let's the function name should be function which take root node, and in our uh, nodes we will see that we have to pass a level which is currently at 0. Suppose let's make a level variable. Okay, so we have to pass our level which is currently 0, then our vector array. Okay, so now let's make the function. Let's make the function private. Our function will return, and it does not return anything. So function, it will take parameter pre-node which is root, another one is integer level, and another one is vector answer. Okay, vector answer. Vector answer, and it should be, I think, vector in, it should be answer. Okay, and it should be passed through a reference. Okay, so we take care of that. If it is not passed through a reference, so you can return our vector and capture it here by answer equal to vector, and return the vector from here. Okay, simple. So let's undo this. Okay, so this is a pretty much function. First of all we have to check whether our root node root node is not is null. If it is null, then return. And then after that we have to check whether our uh, whether our level, yep, whether our level is equal to answer dot size or not. If it is equal, then we have to push that answer dot push back. What we have to push? What we have to push? We have to push root dot not data. Here it is value. As you can see, it is given a value. So simple. If both the condition are not true, then we have to first of all we have to call our right side of the tree root right, and after that we have to increase our level by one, and pass our answer vector as it is. Simple. Let's make duplicate, and after that we have to pass our left side of the tree. Simple. Let's try to run this code. This is basically right part, and this is basically right part. If you, and let me correct it. This is our left part, left. Okay, simple. Fu, it here should be 1. Okay, there are some spelling errors. So fun ctiun. Yep, it is correct now. Let's see. Yep, it is. Let's try to submit it. Yep, it is accepted. Runtime 00, faster than 100%. Okay, so let's talk about what is the complexity again. There is some, I think I done some mistake in calculating the space complexity. Let me rewrite. Yep. So here we calculated the space complexity of big of 1. So it is wrong. So sorry for that. The space complexity, let's calculate the space complexity. First of all, we have to make an array, vector array, which gonna take all the right side of the node. So it's what it's basically take the height of the tree. Okay, so height of the tree is basically log n. Okay, simply log n. The space complexity will be big of log n. Okay, big of log n. So we let it will be little bit take care of that, but this is the space complexity, but we have to add it with the our stack space which we are using in this part. So what we are using actually text space of stack space of log n, also log n. Okay, so basically we are traversing one by one till the height of the tree. Okay, so it will be log n, so it's basically becomes log n also. Okay, so time complexity will be big of n, and space complexity will be for text space, it will be added up with our space complexity of vector, which is log n. So it's basically uh, comes to a log n constant 2 plus 2 times of 2 plus of log n. So it's become log n, big of log n. Simple. Okay, so thank you.